Assalamu alaikum. In this lecture, we are going to talk about the application of directional relay in three-phase feeder. In the last lecture, we talked about a single line to ground fault. But in this lecture, we are going to talk about the line to line faults. That what will happen to the phasor representation of the directional relay if we have a line to line fault in the system, right? So starting the explanation for the phasor for the line to line fault, first we have to talk about the phase faults. Like in this case, if we have a phase fault which is involving phase A, we have 6 different type of faults that are related to the phase A, which is AB fault, ABG fault, so this is double line to ground fault. Then we have CB or BC fault or CBG fault, and lastly we have a three-phase fault, three-phase to ground fault. So these are the 6 different type of faults that can involve the phase A. So we have to decide that for the directional relay, what should be the ICC and what will be the VPC, the polarizing quantity, and this is the signal to the trip content. So as the fault we are going to assume is AB fault, so there is a current that is flowing from A to B. So if we are considering the current IA, then if we will assume it from the B side, that will be minus IB, because if we have, for example, this system in which we have 3 phases, this is IA, this is IB, and this is IC. So if we have a line to line fault and the fault is occurring between the 2 phases A and B, then there is a chance that the current is flowing from A phase to B phase. But if we will consider it from the B phase side, it will be equal to minus IA, or minus IA is equal to IB. So what we are assuming that this ICC will be equal to IA. And now we have to decide the potential coil voltage, which is the polarizing quantity. And we already know that we have to put line to line voltage in place of the polarizing quantity. Line to line voltage, and we have 3 different type of voltages: VAB, VBC, and VCA. And we will be drawing the phasors with respect to VAB, VBC, and VCA, putting each of them as a polarizing quantity in the phasor diagram. And the one that will be suitable for the directional relay will be decided at the end of the lecture. We already know that what are the basic requirements of the directional relay. The first one is that it should operate for the forward faults and should not operate for the reverse faults, right? And it should be secure, which means that it should not operate for the faults which are outside the zone. So it should be secure. So these are the 3 basic requirements for the directional relay to operate securely. This is the phasor diagram for the voltages and currents before and after the fault has occurred. And in the first case, we are assuming VAB as the polarizing quantity, right? So this is your phase voltage VA, and the current IA is in phase with VA. It means that we are considering the unity power factor condition. And by unity power factor we mean that the voltage and current are in phase. So the power factor angle phi will be equal to 0. Similarly, at 120-degree angle we have VB and IB is in phase with VB. And again 120-degree apart we have VC and the current IC. We also have the voltages, line to line voltages as the sides of the triangle. So this voltage is VAB, this is your VCA, and this is your VBC. All these voltages are pre-fault voltages. But once the fault occurs, we have a fault current IAF. Before fault, the current was in this direction, but after fault, the current phasor is shown by this orientation. Now after the fault, the line to line voltages will change. This is your VCA, this is VBC, and this is VAB fault. So now we have to draw the phasor diagram to check whether we can use this VAB as a polarizing quantity or not. It is already decided that ICC is actually equal to IA because we are considering the fault that are related to the phase A. So now the starting point is that first we have to draw the polarizing quantity or the reference quantity, and in this case we are considering VAB. So the direction of VAB is this. So this is your VABF, and from that VABF at 10 to 20 degree we have MTA line. So this is your MTA line at an angle tau with the polarizing quantity. And to define the zero torque line, it will be at 90 degree with MTA line. So this is your zero torque line, and this region is your restraint region for the directional relay, and the region in the direction of MTA line is trip region. So if the fault current is in the trip region, then the relay will operate, and we can consider this VAB as a polarizing quantity. And we know that this is your fault current. So if you draw the fault current, this is IA-F, and this is your zero torque line. So the current phasor is in the restraint region. So we cannot consider this VAB as a polarizing quantity. So we have checked for the voltage VAB whether it can be taken as a polarizing quantity or not. Now the other two voltages that can be considered as a polarizing quantity are VBC and VCA. So let's take VCA as a polarizing quantity, right? So this is the voltage VCA pre-fault voltage, and this will be your post-fault voltage. So we will be taking this voltage phasor as a polarizing quantity. So this is the direction of VCA. At 10 to 20 degree we have MTA line. This is your tau. MTA line, and at 90 degree with the MTA line we have a zero torque line. This is your restraint region. Now if we will draw the fault current, this will be in this direction. This is your IAF. So again VCA cannot be considered as a polarizing quantity. Now the last voltage that can be taken as a polarizing quantity is VBC. So this is your VBC after the fault has occurred. So the direction of VBC is this, VBC, right? This is your MTA line, and this is zero torque line, and this is your restraint region. Now if we will draw the fault current, it will be in this direction, IA-F, and this current in the case of VBC as a polarizing quantity is in the trip region. So in case of phase A related faults, if you will take VBC as a polarizing quantity and IA as the current coil current, which is equal to ICC, then this directional relay will correctly identify the direction of the fault current, whether it is the forward current or the reverse current. So we have checked VAB, VCA and VBC, and we found out that VBC is the polarizing quantity if we have a fault related to phase A, and this is the phasor diagram while considering VBC as a polarizing quantity. And this connection, this particular connection in which IA is equal to ICC and VBC is equal to VPC, voltage of the potential coil, we call it a 90-degree connection, right? Why do we call it 90-degree connection? Because when we take the pre-fault current IA and pre-fault voltage VBC, there is an angle of 90 degree between these two phases. VBC and IA has an angle of 90 degree, and in 90-degree connection related to phase A, IA and VBC will act as the two inputs for the directional relay in order to detect the forward fault. Similarly, we can have different type of connections. Like we talked about IA, the polarizing quantity was VBC, but if we have to find the polarizing quantity for the faults related to IB, we have to use VCA as the polarizing quantity, and in order to detect the fault related to phase C, we have to use VAB as a polarizing quantity for 90-degree connection. Similarly, we have defined the same ICC and VPC for 30-degree connection and 60-degree connections. Thank you.